Okay, so for this video, we're going to go over a problem from 1992 Putnam, problem B1. So this is not a particularly difficult problem. So the question is asking that we have n distinct real numbers. So let's write it down, A1 through AN. And A sub S is the set of all numbers that occur as averages of two distinct elements of S. So we take two elements of S, we take the average, so AI plus AJ, and then divided by 2, where I is not equal to J. So we take this set, and the question is, what is the smallest possible number of elements in AS? So this is AS, and the question is, what is the minimum of the size of AS? So how many elements can we guarantee that AS must have? And so for that kind of thing, we need to show two things. First of all, we have to first find the number. Let's say we find that the answer is n. Then we'll have to show every such set A sub S has at least n elements. And then we'll have to come up with an example of a set of n elements so that the averages are all n. So that's what we need to do. Okay, and this example gives us that n is at least 2 because otherwise you can't really take the average. So one thing that I do notice before I start doing anything is that this over 2 is not really relevant, because when I'm taking the average and I'm comparing the numbers, then I could just simply multiply all of the averages by 2 so that I can just work with the sums rather than averages. So that doesn't make a lot of difference, but it might help like kind of put things into perspective. So as usual, I'll start from some examples. If n is equal to 2, then I have two numbers and their sum is going to be 1. So the answer here would be, the sum would be there's just one sum here. So the answer is 1. If I have three numbers, A1, I'm going to put them in order because that helps me understand how many elements I have. So what would be the order of them? A1 plus A2 is the smallest one. Then A1 plus A3 is the next one, and A2 plus A3. Okay, so this just gives you exactly 3. So this is really not gonna have any element that is repeated. So there's always going to be 3 and nothing else. Starting from n equals 4, there might be possibilities of repetition. So we have A1, A2, A3. So the smallest elements that we're gonna get are A1 plus A2, then A1 plus A3. Oh, there's A4 here that I missed. So the elements are going to be A1 plus A2, A1 plus A3, and A1 plus A4. Okay, so for sure I know that there are 3 elements. But then after that, you could start getting larger, although there might be some things that you wouldn't know whether they are, which one is smaller. Something like A1 plus A4 and A2 plus A3, you can't really know which one is smaller. So, but so far, we do know that we have at least A1 plus A2, A1 plus A3, and A1 plus A4. So now, let's see if we can find something larger. Well, of course we can. At least the least that we can do is that we could change A1 to A2. And similarly, we could take A2 and make it to turn it to A3. So the answer is, so far, we were able to find 5 different, 1, 2, 3, 4, and 5 different numbers in that set, in A sub S, or I guess in double A sub S, because I multiplied everything by 2. So I can say that there's at least 5 elements, but I have to come up with an example. Is it possible to come up with an example that it has exactly 5 elements? If you think about this, if you take things like 1, 2, 3, 4, then the sums would start from 1 plus 2. That's the smallest sum, which is 3. and the last one would be 3 plus 4. So it goes from 3 to 7, and that in fact is 5 numbers. Okay, so the answer for n equals 4 is 5. If I look at n equals 5, I would be able to find a similar story. So I'd be able to do a1 plus a2, a1 plus a5, and then increase a2 plus a5, increase a2, a1 to a4 plus a5. I guess there's just one element here, a3 plus a5. So I started from a1 plus a2 to a1 plus a4, a1 plus a5. So that is 5 elements, and that's 3 elements, so the total is 7. And I should be able to get 7 by taking by taking 1, 2, 3, 4, 5. The smallest number is 3, and the largest number is 5 plus 4, which is 9, and that's exactly 7. So I have something that gives me 7, and I know that there's at least 7 for every possible set S. Therefore, the answer is 7. Okay, so that's not difficult to see the pattern. So 1, 3, 5, 7, those are just odd numbers. Okay, so we'll turn that into a solution. So the first thing I'm going to do is I'm going to write down my answer. So the answer is 2n minus 3. So clearly, these are odd numbers. For n equals 1, n equals 2, it gives you 1. So you would have to do 2n, but then you have to subtract 3 to get to 1. And then it increases by 2. So the common difference is 2. First term is 1. You can see that it's 2n minus 3. Okay, so here's what we're going to do. So let S be, we have always 2 things to show if you want to find the maximum or minimum. First, all of the sizes of AS are at least 2n minus 3. And second, we have an example that 2n minus 3 is obtained with A1 less than A2 less than AN. Note that A1 plus A2 all the way to A1 plus AN, A2 plus AN, all the way to AN minus 1 plus AN, or so n minus 1 from the first terms and n minus 2 from the second set of terms. Distinct sums of pairs of elements of S. Thus, A sub S has at least 2n minus 3 elements. If S is equal to 1 through n, then the sums of pairs of elements of S are integers not less than 1 plus 2 that do not exceed n minus 1 plus n. Thus, there are no more than 2n minus 1 and then minus 2. 2n minus 3 pairs of sums. I guess sums of pairs I meant. 2n minus 3 sums of pairs of elements of S. Therefore, A sub S has at most 2n minus 3. Okay, so maybe I'll let I'll change the name of that to S1 or S0, maybe something that makes it clear that for this specific one I have that. By the previous part, A sub S0 must have 2n minus 3 elements. This completes the proof. Okay, and that completes the proof of that. So just be careful that whenever you're proving things like this, maximum, minimum, you have to do two things. You have to show everything is greater than or equal to the number that you're claiming, and that number can be obtained.